Good morning, everyone. I'm Sheikh Shoaib Akhtar from Department of Mechanical Engineering. Today, my topic is static and kinetic friction in precision machine elements. Now, moving to this topic, first we have static friction. Static friction resets the intuition of motion between two surfaces in contact. It acts when there is no more relative motion. Its magnitude increases with applied forces. Static friction reaches a maximum value just before motion begins. This maximum depends on surface roughness and normal force. It prevents united movement in machine elements. In precision systems, it helps maintain position. However, excessive static friction causes difficulty in motion intervention. It leads to controlled died zones. Static friction is often unpredictable at micro motion levels. Kinetic friction. Kinetic friction acts once relative motion has started. It obsesses sliding motion between contacting surfaces. Its magnitude is generally lower than maximum static friction. Kinetic friction remains approximately constant during motion. It causes energy loss in the form of heat. In precision machining machines, it affects smoothness of motion. Stable kinetic friction is desirable for accuracy. Variation leads to speed fluctuations. It also contributes to wear of components. Proper control improves system efficiency. Mathematical representation. Static friction is represented as F into S mu Sn. Here is mu S is coefficient of static friction and represent the normal reaction force. Maximum static friction occurs at F into S is equal to mu S into N. Kinetic friction is represented as Fk is equals to mu Kn. The coefficient mu k is usually smaller than mu s. This coefficients depends on material properties. Surface roughness affects their Lu- values. Lubrication reduce both coefficients. These equations are fundamental in mechanical analysis. Precision machine elements. Precision machine elements operated under tight tolerance. Examples include linear guideways, leads, secures, and bearings. Motion often occurs at very low speeds. Static friction dominates at motion start. Kinetic friction governs steady motion. Small friction variations affect accuracy. Precision machines require predictable friction behavior. Sudden transmission causes position, positioning errors. Designers must carefully consider friction effects. Friction modeling is essential in high precision systems. Now moving to stick slip phenomenon. Stick slip occurs due to the difference between static and kinetic friction. These systems al- alternates between static and slipping Static friction holds on the surface until forces exceed a limit. Sorry. A sudden slip occurs once motion starts. This results in jerky motion, slip reduce positioning accuracy. It generates noisy and vibration. It is common at low speeds. Precisions machining are highly sensitive this effect. Eliminating stick stick slip is a key design objective. Effect on positioning accuracy. Static friction affects internal displacement accuracy. High static friction creates motion dead zones. Control systems struggle to intimate movement smoothly. Kinetic friction affects continuous motion accuracy. Vibration cause uneven velocity. Precision stages require smooth transmission. Friction induce errors, reduce repeatability. Microscale positioning is specially affected. Accurate control requires friction composition, hence friction directly limits precisions. Surface roughness and materials. Surface roughness strongly influences friction. Surface roughness strongly influences friction behavior. Rough surfaces increase static friction. Smooth surfaces reduce friction but may increase adhesion. Material pairing affects friction coefficients. Metal to metal contact behaves differently than polymer metal contact. Coatings helps reduce friction vibration. Hard coatings improve wear resistance. Soft materials damp vibration. Surface engineering is critical in precision machinings. Proper selection improves performance and lifespan. Rule of lubrication. Lubrication reduces both static and kinetic friction. It creates a thin film between surfaces. This minimizes direct contact. Lubricants reduce wear and heat generation. Boundary lubrication is common in precision systems. Proper lubrication reduces static slip indicate. Lubrication increases friction. Excessive lubrication may reduce stiffness. Lubricant viscosity affects friction behavior. Selecting the right lubricant is external. Application. Static and kinetic friction affects many precision applications. CNC machines tools require smooth guideway motion. Robotic joints rarely on controlled friction. Precision bearings minimize friction vibration. Linear stages needed. Aggregate positioning. Aerospace aggregate operator operate under strict tolerance. Medical devices require high precision. Semiconductor manufacturing demands ultra smooth motion. Friction control improves reliability. This application highly the importance of friction analysis. Methods to control friction. Several methods are used to control friction affect surface finishing, improves contact behavior. Lubrication stabilize friction coefficient. Ruling elements reducing sliding friction. Preloading reduce vibration and backlashes. Advanced materials reduce friction sustainability. Surface coating lower friction levels. Feedback controls components friction effects. Design optimization minimizing friction impact. Active control system improves accuracy. Conclusion. Static and kinetic friction play a circular role in precision machining elements. Static friction controls motion inversion. Kinetic friction governs motion during operation. Their difference causes static slip behavior. This affects accuracy, stability, surface properties, and materials or improvement. Lubrication significantly improves performance precision. Machining requires predictable friction behavior. Proper design minimize friction induced errors. Understanding friction enhance system reliability. Thank you.